radar masts, bow thrusters, wet exhaust systems, marine night vision, deck showers. When you actually sit down and look at the sheer catalog of parts that goes into a boat or, an RV, it really hits you.
Oh, yeah. It's completely overwhelming.
Right. I mean, you aren't just driving a vehicle at that point. You are essentially operating a wildly complex microcity.
It is staggering when you break down the actual infrastructure required to keep those vehicles moving. I mean, you are looking at thousands of interdependent components.
Yeah.
And they're all just, bouncing down a pothole-filled highway or bashing through 6-foot ocean waves.
Exactly. And you can have all the high-tech marine night vision and, advanced thrusters in the world, but none of that gear matters if you are miles from civilization and you can't get a single drop of drinking water to come out of your galley faucet.
No, that's the quickest way to end an expedition, for sure.
It really is. So amidst all that overwhelming complexity, today's deep dive is about mastering one of the absolute most vital, life-sustaining systems on board, the fresh water supply.
Yes. The lifeblood of the rig.
Yep. Specifically, we are unpacking a step-by-step guide to installing a Shurflo water pump.
And, it is a highly specific piece of hardware, but it's one that carries a massive non-negotiable responsibility.
Right, because without it, you're just carrying around a heavy tank of stagnant water.
Exactly. That little motor and pump head, they essentially serve as the beating heart of your entire mobile plumbing system.
And whether you are replacing a tired, sputtering old pump on a camper van you've had for years, or, you're outfitting a literal yacht from scratch, understanding this process is just huge.
It completely changes the game.
It does. It turns what looks like a really daunting, messy plumbing task into an incredibly empowering DIY project because you are taking complete control of your water supply.
What's fascinating here is that installing this pump isn't just about turning screws and blindly attaching hoses.
Right. It's way deeper than that.
It really is. It is a masterclass in understanding the delicate balance of fluid dynamics, electrical engineering, and acoustic vibration management.
Wow. Yeah. All of that just to get water out of a tap.
Yeah, because that balance is what keeps your mobile adventures going comfortably. You are literally building a tiny, self-contained, pressurized infrastructure.
So before we start cutting hoses or stripping wires, you have to gather your arsenal, right? And you have to find the perfect physical environment for this pump to live.
Yeah, the setup is half the battle.
For sure. So you need your standard basics like a screwdriver or a drill, an adjustable wrench, stainless steel hose clamps, and Teflon tape. But the real puzzle, at least from what I read, is the location.
Oh, absolutely. Location is everything.
Yeah. The source material lays out some strict requirements here. The space needs to be a flat, stable surface. It must be well ventilated, protected from extreme heat and moisture, and crucially, positioned below or close to the freshwater tank or the wet bay.
The real estate matters just as much as the hardware itself. I mean,
Yeah,
if you take a brilliantly engineered pump and you just stick it in a terrible location, it will fail prematurely, without question.
Okay, let's unpack this. Because picking a spot for the pump, to me, it feels like placing a delicate organ in a body.
That's a good way to put it.
Right. Like, it needs to be protected, but it also has to be perfectly positioned to actually do its job. But the guide heavily emphasizes this idea that it must be positioned below or close to the freshwater tank. And I have to push back on that a bit.
Okay, why is that?
Well, space is at an absolute premium in a van chassis or a boat hull. Why not just tuck it away up in a ceiling cabinet or wherever you happen to have a few cubic inches of dead space?
I get that instinct, but it really comes down to the brutal realities of physics.
Physics always ruining the fun.
Always. Pumping water is literally lifting weight. Water weighs over 8 pounds per gallon.
Which is heavy when you're moving a lot of it.
Exactly. So proximity to the tank, and specifically being situated below the water level of that tank, utilizes gravity to do the heavy lifting for you. This is a concept known as head pressure.
Okay, so if you mount the pump high up in a cabinet, it has to fight to pull that weight upwards before it even pressurizes the lines.
Right. You are forcing the pump to pull a deep vacuum just to get the water up to the inlet.
Which it isn't designed to do.
Well, these Shurflo pumps are positive displacement diaphragm pumps, meaning they are exceptionally good at pushing water out under pressure, but they are not designed to be massive vacuum cleaners on the intake side.
Oh, I see. So pushing is easy, pulling is hard.
Exactly. If you force it to suck water up from a tank located far below it, you are making that motor work much harder than necessary. You increase the amp draw, you generate excess heat in the motor, and you dramatically shorten its lifespan.
Wow.
Yeah, but by placing it below the tank, gravity naturally feeds the water down into the pump's inlet. Then the pump gets to focus 100% of its mechanical energy on pushing the water out to your shower heads.
Work smarter, not harder. Let gravity feed the machine.
Exactly.
And regarding the protection from heat and moisture, which, might seem slightly counterintuitive since we were talking about a water pump, the guide is very firm on this.
You have to remember, it is an electromechanical device.
All right, electricity and water, famously bad friends.
Yeah. It has a copper wound motor and sensitive electrical terminals. So extreme ambient heat in a closed, unventilated compartment, say, right next to a hot engine block, can cause the motor's internal thermal breaker to trip during heavy use.
And then your shower just stops halfway through.
Exactly. And on the flip side, external moisture from, like, a damp boat bilge can quickly corrode the electrical spade connectors. The goal is to give this crucial piece of hardware a cool, dry, easy life.
So we've mapped out our perfect, cool, low-altitude real estate. The pump has a home. Now it is time to build its circulatory system.
The plumbing.
Yep. We are routing the plumbing and connecting the water hoses safely and securely. The physical sequence is pretty straightforward. You connect the inlet hose coming from your freshwater tank to the pump's inlet port, and then you attach the outlet hose to carry the newly pressurized water out to the system's faucets and appliances.
It sounds simple, but the devil is entirely in the details here. The materials and methods you use are absolutely make or break.
Right, because nobody wants a flood in their van.
No. That's why stainless steel hose clamps over flexible tubing are mandatory to prevent blow-offs under pressure.
Yeah, clamps are obvious. But here is something that caught my eye in the installation guide. It strongly dictates adding an inline water filter, usually this little transparent strainer, directly at the inlet port of the pump.
Yes, highly recommended.
I look at that and think, if I am using clean municipal water and I just filled my fresh water tank from a clean drinking hose at my house, putting a filter right before the suction side of the pump seems like creating a bottleneck.
I hear that a lot.
Isn't that just adding a dirty sponge that will starve the pump of water?
It is a really common misconception that filters automatically restrict flow. The inline strainers designed for these pumps use a really fine stainless steel mesh with a large surface area.
Okay.
Unless you completely neglect it and let it fill with mud, it won't restrict the flow rate at all. And more importantly, that inline filter is the ultimate non-negotiable defender of the system.
Defending against what exactly? If the water went in clean in the first place.
Think about the physical reality of a mobile water tank.
Yeah.
The vehicle is constantly moving. The water is violently sloshing around for hours on end.
Oh, sure, like a giant washing machine.
Yeah. And over time, that friction breaks things loose. You get calcium scale buildup flaking off the tank walls, tiny bits of particulate matter from campground water pedestals, or even microscopic plastic shavings left over from when the manufacturer first drilled the fittings into the tank.
Oh, wow. I didn't even think about manufacturing debris. And all of that suspended debris is heading straight down the pipe into the pump.
Straight into highly sensitive internal mechanisms.
Yikes.
Inside that Shurflo pump is a flexible rubber diaphragm with multiple separate chambers and tiny precision-molded check valves. These valves operate with incredibly tight tolerances, snapping open and closed rapidly to build water pressure. If even a single grain of coarse sand or a tiny shard of hard plastic gets sucked in and wedged into one of those valves...
The valve can't close.
Exactly. The valve can no longer close completely. The pump immediately loses its internal seal.
So the pressure just bleeds right back out into the tank.
Yep. The system essentially chokes. The pump will run constantly because it can never reach its shutoff pressure. Your shower flow drops to a trickle, and the motor eventually burns itself out.
That sounds like an expensive mistake.
It is. The inline filter acts as a physical barrier, catching that rogue debris before it ever reaches the delicate mechanics.
Okay, so a $15 transparent strainer is essentially a cheap insurance policy to protect a highly engineered pump head. That makes total sense. Now, let's talk about the actual threaded connections, because the guide specifically calls out the use of Teflon tape.
I cannot overstate the importance of proper thread sealant. It is fundamentally misunderstood by a lot of first-time DIRs.
Yeah, I think people assume it's literally tape like duct tape, just holding the pipes together from the outside.
Exactly. But it is actually PTFE polytetrafluoroethylene.
That is a mouthful.
It is. But basically, it's a highly malleable lubricating film. The plastic or metal threads on plumbing fittings, no matter how well machined they are never perfectly mated.
Right, there's always a tiny gap.
If you look at them under a microscope, there is always a spiral gap between the male and female threads. And when your system pressurizes to 45 psi, water will absolutely find that spiral path and push its way out.
Because water always wins.
Always.
Every time.
So what does the tape actually do?
When you wrap the male threads with Teflon tape, the action of screwing the fittings together crushes and shears that soft PTFU material, forcing it to cold flow directly into those microscopic imperfections.
Oh, so it fills the gaps completely.
It completely blocks the spiral leak path. This prevents the slow, invisible weeping leaks that could easily rot out the plywood subfloor of your RV or the structural stringers of your boat over a 6-month trip.
That is a terrifying thought, ruining the entire structural integrity of your vehicle over a single drop of water escaping every hour. Wrap the threads.
Always wrap the thread. All right, so the water is routed and sealed, but right now it is just a static dead pipe. To actually create the pressure that makes this a circulatory system, we have to introduce electricity and physical movement.
Right, bringing it to life.
We are talking mounting the unit, running the positive and negative wires to your 12-volt or 24-volt battery bank, and wiring in a fuse.
This is the critical intersection where plumbing meets mechanical and electrical engineering.
And I want to zero in on a very specific instruction from the text regarding the physical mounting. The manual explicitly says, avoid over-tightening to prevent damage.
Yes, very important.
When I first read that, my instinct was, wait, this thing is going in a violently moving vehicle. Shouldn't I bolt it down like a bank vault? But then I realized mounting this pump isn't about bolting it down immovably. It is more like installing shock absorbers.
That is the perfect analogy. The pump comes with thick, flexible rubber mounting feet for a very specific reason.
So if you take your wrench and torque those bolts down until the rubber feet are crushed completely flat against the floorboard, you strangled it.
You've completely defeated the purpose of the feet.
Right. Because the vibrations from that high-speed motor have absolutely nowhere to go except directly into the solid structure of your vehicle.
And the acoustic result of that mistake is just unbearable. A rigid, over-tightened mount turns your entire van chassis or boat hull into a giant acoustic amplifier.
Oh, so it just echoes everywhere.
The structural panels act like a speaker cone for the pump's motor vibration. It will sound like a jackhammer going off inside your cabinetry every time someone flushes the toilet.
Nobody wants that at 3 a.m.
Exactly. By securing the screws just until they are snug, you let those rubber feet retain their shape. They isolate the vibration, absorbing the mechanical energy before it can transfer into the floor. Let the rubber breathe.
Snug, but not crushed.
Mm-hmm.
Got it. Now, let's look at the electrical side. The guide is adamant about using the proper gauge wire and installing a dedicated inline fuse on the positive wire as close to the power source as possible.
Essential step.
But I have to play devil's advocate here. I get having a fuse at the main breaker panel of the RV. But the guide insists on a dedicated inline fuse specifically for this circuit. Why the redundancy? It's just a 12-volt battery system.
Well, if we connect this to the bigger picture, you have to look at how DC power behaves, especially under stress.
Okay.
In a mobile environment, wire runs can be surprisingly long, maybe 20 or 30 feet from the battery bank to the water pump. If you use wire that is too thin, you create electrical resistance.
And resistance is bad.
Resistance creates a severe voltage drop, meaning your 12-volt pump might only be receiving 10 volts by the time the power actually reaches it. That starves the motor, causing it to run hotter and pull even more amperage to try and do its job.
Just a vicious cycle of heat and inefficiency.
Exactly. And that leads directly to the fuse redundancy. Say a piece of debris does get past the filter and locks up the diaphragm.
Okay, the pump gets stuck.
The motor stalls. A stalled electric motor instantly pulls what are called locked rotor amps.
Locked rotor amps, what is that?
It's a massive sudden spike in current as the motor desperately tries to turn against the blockage.
Oh, so it's pulling as much juice as the battery can physically give it.
Exactly. If that spike happens, the thin wires leading to the pump can rapidly overheat, melting their insulation and potentially starting a localized fire inside your wooden cabinetry long before the main breaker at the far end of the vehicle realizes there's a problem.
It is terrifying.
It is. The dedicated inline fuse acts as a bodyguard. It is sized specifically for the pump's maximum safe amp draw. It sacrifices itself, breaking the circuit instantly and protecting both the expensive pump and your vehicle from catastrophic thermal damage.
It takes the bullet so the wiring harness doesn't have to. I love that. Okay, so the physical installation is complete. The pump is plumbed, filtered, softly mounted on its shock absorbers, and electrically guarded.
You're almost there.
But you can't just flip the power switch and walk away to take a shower, right? Breathing life into the machine for the first time requires a very specific, careful sequence. You are priming the system.
This is where the physics of fluids really comes into play. It is the moment of truth for the installation.
Yeah, the guide walks through this process. You have to open all the connected faucets, hot and cold, fill the fresh water tank, then turn on the pump and let it run.
Yep, exactly.
And you wait until water flows smoothly out of the taps, sputtering at first, then steady. Only then do you close the faucets to test if the pump automatically shuts off. But I want to know about the mechanics here. Why is opening the faucets before turning the pump on so critical? What happens if you forget, leave the taps closed, and just flip the switch?
If you leave the faucets closed, you are asking the pump to move water into a closed loop of plumbing that is already completely full of atmospheric air.
Right. The pipes aren't empty, they're full of air.
Exactly. Think about the fundamental difference between the two states of matter. Air is highly compressible. Water is largely incompressible.
Okay, so the pump turns on, and it pushes against the air in the lines.
The pump pushes, the air compresses, acting like a giant invisible spring, and that trapped air creates immense back pressure against the pump head.
Oh.
Because the pump is fighting that compressed air on the outlet side, it struggles to pull a sufficient vacuum on the inlet side to draw the heavy water up from the tank.
It's like trying to suck liquid into a syringe while your thumb is tightly covering the tip. You pull the plunger, but nothing moves.
That's a great example. It strains the motor, and crucially, it forces the internal rubber diaphragm to run completely dry at high speeds, which generates friction heat and can severely damage the components.
Just by leaving a faucet closed.
Yeah. But by opening the faucets first, you give that trapped air an easy escape route. The pump turns on, the air is freely pushed out of the open taps, and with zero back pressure, the pump easily creates the vacuum needed to pull the heavy water smoothly up from the tank.
And once solid water is flowing steadily out of the faucets without spitting or hissing, you know the air is successfully purged. And then comes my absolute favorite part of the entire process, the final test. You walk around your vehicle, you shut off the galley sink, you shut off the bathroom vanity, you close the shower head, and you stand there and wait for the sound.
The click.
Yes, the click. The pump runs for just a few seconds more. You hear the pitch of the motor change as the lines pressurize, and then click. Total silence. It shuts itself off completely.
It is an incredibly satisfying milestone. That silence is the ultimate proof that you have succeeded.
What's actually making that click happen?
Inside the head of that Shurflo pump is a small pressure switch. As the water has nowhere to go, the pressure builds up in the lines, physically pushing against a small diaphragm that triggers a micro switch, cutting the electrical circuit.
That's so clever.
It is. When you hear that silence, it means your Teflon tape is holding, your hose clamps are tight, there are zero leaks in the plumbing, and the internal pressure switch is calibrated perfectly. You have built a closed, pressurized, self-regulating infrastructure.
You are officially a master of mobile plumbing.
Indeed you are.
But the guide doesn't stop at just getting it running. A true DIY master thinks about how to optimize the experience and keep the system alive for years to come.
Oh, definitely. Maintenance and upgrades?
Yeah, the sources detail advanced tips for long-term survival, like inspecting your hoses for chafe marks, regularly cleaning that inline stainless mesh filter so it doesn't become the bottleneck we worried about, and winterizing the pump. But here's where it gets really interesting. They detail the massive benefits of pairing the pump with an accumulator tank, as well as integrating city water connections.
These are brilliant additions to any mobile water system. They fundamentally change how the plumbing feels to use.
Taking it from a rugged camping setup to a refined residential experience.
Exactly.
Let's start with the accumulator tank. The way I read it, this is essentially a luxury upgrade to smooth out the water pressure. Because without it, if you turn the bathroom faucet on just a tiny little bit, say a slow trickle to wash your hands or brush your teeth, the main water pump is frantically turning on and off, multiple times a second, right?
Yes.
Just violently stuttering to match that tiny flow rate.
That phenomenon is called rapid cycling, and it is the absolute enemy of any diaphragm pump.
Let's break down the mechanics of why that happens.
Well, the pump's internal switch is set to shut off at, say, 45 psi. When you open the tap, just a tiny fraction, the pressure in the line drops instantly. The pump detects the drop and kicks on.
Makes sense.
But because the tap is mostly closed, the powerful pump instantly repressurizes the line back to 45 psi in half a second, and the switch cuts the power.
Oh, and then a split second later, the trickle at the faucet drops the pressure again, and the pump slams back on.
Exactly. It is violently starting and stopping the heavy motor, which burns out the microswitch contacts and stresses the plumbing joints. Not to mention, it is incredibly annoying to listen to that machine gun sound in the middle of the night.
Seriously. So how does the accumulator tank solve this?
An accumulator tank is a small, sealed metal or plastic vessel that you plumb into the system right after the pump. Inside this tank is a flexible rubber bladder. Behind the bladder is a pre-charged cushion of compressed air.
Okay, so it's like a little reservoir.
Yeah. When the main pump runs, it pushes water into the accumulator tank, expanding the bladder and compressing the air cushion further.
Storing the pressure.
Exactly, storing the potential energy. So when you wake up at 2 a.m. and open the tap to brush your teeth, the water you are using comes entirely from the pressurized reserve inside the accumulator tank.
Oh, so the compressed air just pushes the water out smoothly.
Right. The main pump doesn't even need to wake up. You get totally silent water delivery for those small, quick tasks. And when you finally use enough water to deplete the accumulator like taking a shower, the main pump turns on and runs smoothly and continuously to refill the system. It eliminates the stuttering entirely.
That is genius. It turns a noisy RV sink into a luxury hotel experience.
It really does.
Now, the outline also touches on city water connections. This is a totally different way of getting water into the vehicle.
It is a parallel system that bypasses the tank and the pump entirely. When you pull into a developed campground or a marina, you can hook a pressurized hose directly from the dock or pedestal to the side of your vehicle.
But wait, if I'm hooking up to municipal water, which can be blasting at 80 or 90 psi, isn't that going to blow my RV's 45 psi plumbing system completely apart?
That is the real danger, which is why a city water connection must utilize a pressure regulator at the inlet. You have to step that aggressive municipal pressure down to a safe 40 or 45 psi. Furthermore, you rely heavily on the internal check valves inside your Shurflo pump.
How so? Like, why does the pump matter if I'm bypassing it?
Because when the city water pressurizes your lines from the outside, the water wants to flow backwards through your pump and into your fresh water tank.
Oh, which would eventually overflow and flood your vehicle.
Exactly. The precision check valves inside the pump head physically block that reverse flow, separating the pressurized city water from your stored tank water.
The engineering is brilliant. Everything relies on these tiny, unseen barriers.
It's a delicate balance.
And to keep those barriers functioning, the source material hammers home seasonal maintenance. Winterizing is brought up as a critical point for survival.
Which absolutely cannot be ignored, or nature will destroy your hard work. Physics comes back into play with devastating consequences. You see, water expands by roughly 9% when it freezes into a solid crystalline structure.
Which creates thousands of pounds of outward pressure.
Exactly. If you leave water trapped in the pump's diaphragm housing or inside the inline filter bowl over the winter, that expanding ice will effortlessly snap the hard plastic housings and shred the rubber valves. Your pump is instantly destroyed.
Game over before the spring season even starts.
Winterizing is non-negotiable. You either use an air compressor set to a low PSI to completely blow all the moisture out of the lines, or you use the pump to draw non-toxic RV antifreeze through the entire system until the pink liquid flows from every tap.
And that saves the hardware.
These maintenance steps are the difference between a pump that lasts a decade and one that dies violently on your very next trip. It also ensures the pump stays covered by its warranty, because freeze damage is universally denied by manufacturers.
That makes sense. So to quickly recap the journey for you today, by picking the right physical spot that uses gravity to your advantage, meticulously wrapping and clamping the plumbing to banish microscopic leaks, softly mounting the hardware so it absorbs the acoustic energy, wiring in that bodyguard inline fuse to stop thermal meltdowns, and finally, properly purging the air to prime the lines, you've successfully conquered a major DIY milestone.
It is a significant technical accomplishment, and I think it brings us full circle back to where we started. Remember that massive catalog of boat parts from the beginning of this deep dive?
Oh yeah, the radar masts, the thrusters, the night vision systems.
The overwhelming micro city on wheels or waves.
Right.
Mastering this one specific installation, the freshwater pump, fundamentally changes your relationship with that micro city. You are no longer just a passive passenger turning a knob and hoping the water magically flows. You have literally taken control of the lifeblood of your vessel. You understand the pulse, the back pressure, the electrical draw, and the mechanics of how it all works in harmony. It makes you wonder what other vital, unseen systems in your surroundings are just waiting to be understood and mastered by you.